Hi, my name is Kieran Sheila, and I will be presenting my paper on a millimeter wave beam steering antenna based on extended hemispherical lens antenna subarrays. Myself and my advisor, Dr. Gokhan Mumchu, are with the WAMI Center at the University of South Florida in Tampa. In modern millimeter wave systems, phased arrays are prevalent due to the increased need for electronically steerable high-gain antennas, required to satisfy potentially problematic link budgets. Large phased array systems, like those used in base stations, can be quite complex. This is true even more so for hybrid MIMO systems, which, unlike traditional arrays requiring a single phase shifter per element, can require multiple phase shifters per element, one for each RF chain. Every one of those phase shifters will require at minimum control lines, and depending on the architecture, bias lines as well. And on top of all that, all those phase shifters have quite a bit of loss. To achieve the same link budget, we would need amplifiers to compensate for the insertion loss, which in turn increases the array's DC power consumption. One solution to this problem is the utilization of subarrays. By chunking the full array into these subsections, we can reduce the phase shifter count by a factor of the subarray size. And this does a couple things. First, it's important to note that the subarray elements are all fed in phase, each creating a broadside pattern based on their own array factor. And as such, the subarray element spacing is set to the conventional lambda by 2 in order to eliminate grading lobes in the array factor. But then, these subarrays are phased together such that they form the complete array. And by phase shifting each subarray group, we can steer the full array's pattern effectively within the 3 dB beamwidth of the subarray pattern. This solution isn't without its drawbacks, however. Because the subarray pattern is being multiplied with the array factor of the entire array, treating each subarray as a single element, there are grading lobes in the final pattern, as the subarray spacing is much greater than lambda by 2. The solution is then to increase the gain of the subarray pattern, such that after multiplying with the full array's array factor, those grading lobes are suppressed. As we can only really steer within the 3 dB beamwidth of the subarray pattern, increasing the gain decreases our steering capability. And on the flip side, decreasing the gain allows us to increase that steering capability, but at the consequence of increasing the side lobe level due to the full array's grading lobes, generally speaking. Now, there are a few techniques to improve this trade-off, but generally that trade-off increases the array's complexity in some way. Our group's previous work offered one solution to this problem by introducing the concept of lens antenna subarrays. The general idea is that given a subarray, rather than feed all of the elements in phase to create a broadside pattern, we would feed one at a time underneath a dielectric lens, replacing the combinational feeding network with a switch. By selecting an excitation underneath the lens, we can create a high gain pattern whose direction of maximum radiation is controlled by which feed we excite. This allows us to steer the beam of the subarray pattern versus only relying on the broadside pattern of the equivalently sized high gain traditional subarray. Then, as with the traditional subarray-based antennas, we phase shift each lens group to steer the full array pattern around the already steered subarray pattern, bridging the discontinuities between subarray beam directions. Additionally, solid-state switches provide much lower insertion loss than phase shifters, adding to the lower power consumption benefit. Now, this work has already been experimentally proven to provide a significant advantage, with our 38 GHz design steering at plus or minus 37.5 degrees, with a minus 9 dB side lobe level. This previous work, however, focused on steering in a single azimuth. The design uses a 3D printed hemi-cylindrical slab lens and aperture-coupled patch antennas as the feeds. The design was manufactured with 4 lenses and 5 different feed positions, which were measured by mechanically moving the lens over the feeding patch. My job was to extend this work to allow for full 2D beam steering, replacing the slab lens with a lens which provides high gain in every azimuth. We went with a hemispherical lens as it is simply the volume of rotation for the hemi-cylindrical profile. And so this work then outlines the new procedure for creating a lens antenna subarray-based system which works in 2D. The original works' design procedure is as follows. Fix the diameter to the number of feed positions m at lambda by 2 spacing. Then maximize the gain in the broadside direction by adjusting the extension length. Finally, the feed positions were chosen such that all of the steered beams intersect at their 3 dB point to ensure coverage of the lens's field of view. I started by using this procedure on the new lens geometry. I was planning for a 4x4 subarray, so I went with m equals 4, which sets the diameter to 20 mm at 38 GHz. Sweeping the extension height, I found a maximum gain of 17.6 dBi at 12 mm. And the broadside pattern looks really good, but the problem started appearing when I translated the feed off-axis. Here are some pictures of the simulation setup, indicating the primary design geometry. It's important to note that I have to run full-wave simulations here, as the lens is electrically small and high internal reflections make the pattern pretty unpredictable. The most important difference in the results after following the old procedure is the high side lobe level. I simulated worse than -5 dB at certain feed positions. It seems that one origin of the high side lobe level is from the internal reflections, which to me indicates that the old procedure just isn't suited for this new lens geometry. Additionally, we are only looking at the pattern in a single azimuth. There isn't really an obvious single plane cut once we steer the beam off axis, so we will just use a pattern cut in the azimuth of maximum radiation. This normally corresponded with the same azimuth the feed was translated on. In the figure in the lower left, the feed is translated by 7 mm at an azimuth of 30 degrees. We would then suspect that the maximum radiation would also be on this azimuth, and as such prepare the corresponding radiation pattern. The problem is that this doesn't really capture all of the information. We could make observations about max gain and side lobe level based on this cut, but what if there's more going on in another azimuth? We could look at the 3D pattern and scroll around with our mouse trying to look at it from every angle, but that doesn't really allow for much automation. So, one solution is to plot the 3D pattern's contours on a polar plot, as seen in the top right. The primary axis represents azimuth, and the radial axis represents elevation, as if we were looking down into the lens. By selecting one or more contours, like the -7 dB contour plotted here, we can compactly represent some semblance of the full 3D pattern. In this Beamwidth contour plot, one can see that there are side lobes, namely the one labeled 4, whose maximum are not in the azimuth cut of maximum radiation. We would have missed this in the normal pattern plot and would have proceeded thinking that the side lobe level is better than it actually is. So taking these shortcomings into consideration, we designed a new procedure for establishing the geometry of the 3D lens antenna subarray. We first start by fixing the diameter, similar to before, but by adjusting the scaling factor m to the square root of m, representing the diagonal length of a λ/2 spaced square subarray of total elements m. This would give a lens of approximate effective aperture similar to that of the traditional planar subarray. Then we would start the extension height at the optimum hyperhemispherical extension height as outlined in the referenced seminal paper. Next, for patch placement. This part is pretty tricky. Part of declaring success in this design is guaranteeing that we can cover all of the lens's field of view without any discontinuities. In the original paper, this meant positioning the patches such that the resulting lensed half-power beam widths intersected, which represents a single point in constant azimuth. However, in the 3D world, the half-power beam width is a contour. If we want to maximize coverage of the lens's field of view, we have to completely cover the lens's field of view with those half-power beam width contours. This is a classical geometry puzzle called the circle covering circle or disk covering problem. And to use the solutions from this problem, though, we have to make a couple of assumptions. First, we have to assume that the half-power beam width contours are in fact circular. This has been shown to be an adequate approximation, but less so for highly off-axis excitations. Second, we have to assume that the location of the half-power beam width contours in spherical space is geometrically similar to the location of the patches on the focal plane of the lens. Geometric optics is on our side for this one, and has shown to work pretty well. So the idea is that, given m feeds, find the optimum disk covering solution for that m, and place the patches in a similar pattern on the focal plane. We found that a good starting point is with a minimum spacing of about λ/2. So to finalize the design, we simply optimize around this initial geometry. The optimization process really relies on parametric sweeps and interpreting the beam width contour data. So to help in that, I wrote a library called Marconi.jl for the Julia programming language, specifically meant for working with radiation pattern data. For those who don't know, Julia is a new free and open source programming language designed specifically for scientific computing, similar to MATLAB. So parametric sweeps were run in ANSYS's HFSS, and then the bulk pattern data was imported into Marconi, where we can assess all of the performance metrics such as side lobe level, gain, field of view coverage, and so on. Additionally, Marconi has an array factor tool, where in the same beam width contour plot, we can plot what would be the contours in the array context. This includes automatically steering the beam around the single lens's half-power beam width. Depending on the results of those performance metrics, we update the geometry accordingly. As a rule of thumb, manipulating the coverage of the half-power beam width contours usually meant moving the patches on the focal plane. This could even involve adding patches if coverage isn't possible, as was the case in my original m=16 design. If the side lobe level was bad, or the gain non-uniform, modifications were made to the lens geometry itself. Our paper shows a flowchart that describes the entire optimization process in more detail, and we plan to extend that discussion in a future publication. Here at the bottom, we can see the final lens design, the half-power beamwidth contours, and the generated array factor contours. These contours indicate successful coverage of the lens's field of view and allow us to proceed. After the single lens and array factor results looked good, I simulated an entire array, including 3D component models for the K-connectors. And the results turned out to be really good, with the full array patterns matching the array factor patterns. And so in the end, my 38 GHz design achieved plus or minus 40 degree coverage with a worst case side lobe level of about minus 9 dB. And as one can see in the contour plots, certain azimuths can be steered up to 45 degrees. Additionally, gain is pretty high at just over 20 dBi, representing a little under 80% efficiency for the size, and the feeds are all matched to cover the entire FCC 38 GHz band. We then move forward with designing an experiment to verify my results. Here are some images of the manufactured 3-layer PCB and the assembled antenna with the 3D printed lenses and K-connectors. The plan for the experiment is to work off of the center patch in the subarray. The PCB was designed so all the 7 feeds are fed in phase. This is so we can measure the pattern from each lensed subarray and combine them in software, including the phase information. There are 4 configurations to test, based on the 4 repeating patch locations due to rotational symmetry. While we were limited in manufacturing one PCB design, we printed additional lens boards where the lenses are offset by the location of the patches we were interested in. By placing the excited center patch under the lens off-center, we can effectively test the other patch locations. This is similar to the original work, where the patches were translated with a servo, but in this case, there are just 4 static configurations. As we just got the PCBs in the mail, the experiments are currently underway, and we intend to publish our results as soon as we have our experimental data. All in all, we've been pretty impressed with the performance of this new 2D lens antenna subarray technology. Compared with some similar subarray-based antennas, as shown in the table below, the 2D LAS has a very high scan range of at least plus or minus 40 degrees, a low side lobe level of minus 9 dB, all while maintaining a relatively high efficiency of up to 80%. Additionally, the 2D LAS is easily manufacturable with conventional PCB fabrication techniques and a commercial off-the-shelf 3D printer. Our group hopes to expand this work by further reducing the side lobe level, as we think there are still optimizations to be made. Also, we are working towards designing and integrating a switch IC into the LAS design. So, LAS technology is shaping up to be a viable solution for some common subarray-based antenna trade-offs. It offers high scan range at a low side lobe level, all with the subarray benefits of reducing complexity in DC power draw. While the LAS is more complex than the traditional subarray design by adding a switch, we believe that trade-off is worth it to increase the scan range while still reducing DC power consumption. So, thank you so much for your attention. Have a great rest of your day.